Hello, gals and guys. Happy Friday Eve. Mr. Ambrose here with another AP exam review video. Um, as you may notice by the screen, uh, we're going to start off with today is Euler's method. We're going to go over that, and then we'll look at a couple of other just little topics here and there that, again, you could potentially see. So, with that being said, let's take a look at Euler's method. So if you recall, Euler's method actually was a calculation that was used to perhaps try to help approximate particular solutions to a differential equation. And this here being a sloped field with this particular solution drawn out based off of this point here, the idea of Euler's method is that it does use tangent lines to help with that approximation process. So if, say, we're at this point here and perhaps we want to approximate what the function value is at x equals to -1, the idea is that if we start off perhaps with the tangent line at this particular point, which perhaps would look like this here, a single tangent line can be used to help approximate a function, but it only really is good to approximate that function when we're close to where that tangent line is touching our function. Right? Because as we go out further along our curve, the tangent line and the graph diverge tremendously, and the tangent line will no longer be a good approximation tool. But what Euler's method does is that instead of trying to approximate for what is f of -1 based upon the single tangent line, what we do is we use this beginning tangent line to approximate for perhaps what the y value is at, say, like x equals to 1.5. And then from there, we use that approximate y value and the x value 1.5 to get a new tangent line to approximate another y value, and so on. And so if you recall in class, like I showed you this particular slope field with this particular solution, and instead of having just a single tangent line here at this particular single point to help approximate our function over here, right over here, you'll notice there are 45 tangent lines that have been used to slowly approximate, successive y values to ultimately get to a close enough value for what the y value is to our function over here. And so that's the basic idea of Euler's method. It really is just a calculation process, and you can always use the process that I showed you in class that I'm going to do here in this problem to answer any one of these types of problems. So in this question, we want to let k be a constant. We're going to consider the differential equation dy dx equals this kx squared plus y, where y equals to f of x is the particular solution to the differential equation with the initial condition f of 0 is equal to 2. We want to use Euler's method starting at x equals to 0 with two steps of equal size, and f of 1 is approximately 17/4 to solve for k. So again, who knows exactly what you're going to be presented with on your AP exam. While I'm going to use Euler's method ultimately to help solve for k, right, we already know what the start and end points are, but I claim that if we still just perhaps go through that process here, if we are careful with things, we'll ultimately be able to solve what this value k is. So if you recall, the process that I showed you was that I make a table, and I'll have a column for x, a column for my y values, and then I'm going to have a column for my derivative, dy dx equals this kx squared plus y. And then I have a fourth column to put together my equation of my tangent line, right? Because again, Euler's method is just finding a succession of tangent line equations to progress our way to ultimately approximate what the particular solution is to our function. So we start off at the starting point of 0, 2, and I will construct my first tangent line equation. And right, to construct our tangent line equation, right, we need a point and we need the slope. So we already have the point because we're starting at this particular point here. And to get our slope, we can just plug this point into this equation to get our slope. So I plug 0 in for x, 2 in for y. And the nice thing here is that this is just going to be 0, so that'll drop out, and our slope to our first tangent line equation is 2. And using this point again and this slope, I'll put together the first of our tangent line equations. So now to progress to the next particular tangent line, right, we have to know how to progress with our x values or be given some sort of information. And while we're starting at 0 and we're going to get up to 1, we're doing so by using 2 steps. And we pretty much always do equal steps. So to go from 0 to 1 in 2 steps, that would mean our delta x, our change in x value, would have to be equal to 1/2. So the next x value we'll construct a tangent line equation that will be 1/2. And to get our y value, we can use, again, this tangent line equation here to get the y value for this. So I will perhaps just change the color. So I'll take my x value of 1/2, I'll plug it into this equation here, and when I solve for y, we get that y is equal to 3, and now we're ready to start and construct our next tangent line equation. So with x equals to 1/2 and y is equal to 3, we would have that our slope here would be k times 1/2 squared plus 3. And I'll perhaps want to simplify this to be in just 1/4 k plus 3. And so this will be our slope. This is our point. And I will now construct my next tangent line equation. So we'll have y minus 3 is equal to our slope, which is 1/4 k plus 3, and that is multiplied by x minus 1/2. And that whole slope is multiplied to this x minus 1/2, right? Because that's how our point slope form for our equation where our tangent line is, goes, is the way it's set up. But notice I put parentheses around that to properly denote that this whole thing is being multiplied to this. And so now I will perhaps continue this on the next page. So again, we had, actually, I'm just going to go right, actually, I'll do this, 1/2, we had 3, and I'm just going to copy down, we had y minus 3 equals this k 1/4 k plus 3 times x minus 1/2. And our next x value, right, is going to be at 1. And we actually knew what the y value approximately was there. Right? We were told that f of 1 is approximately equal to 17/4. So that's why I'm plugging that in right over here. And so technically, right, while we already were given this, this is how we're going to be able to solve for what this k value is, right? And I just want to make sure I have that down right. So the idea is that we would have plugged 1 into this equation here to ultimately get and solve for what this y value is, right? So I'm just going to copy that over. And we would have plugged 1 in for x, and then we would have, solved for what this all equals in terms of this y value. But they told us that that y value is 17/4, and so now hopefully you'll notice that we can use this expression here ultimately to solve for what our k value is. So, and I'm going to, while you have a calculator technically on your exam to do all this, I'm going to use my mental calculator to quickly solve this. So 1 minus 1/2 is just 1/2. This here ends up being 5/4, and this is going to equal 1/4 k plus 3 times 1/2. We could perhaps now multiply both sides by 2, and we would get 5/2 equaling 1/4 k plus 3. And then if we subtract 3 from both sides, we would get negative 1/2 equals 1/4 k. And then if we multiply both sides by 4, we would get that k is equal to negative 2. All right. So just be mindful if you're asked to, if you're told, use Euler's method and they typically always tell you that in a problem. Even if it's not direct exactly what you're used to finding, just go with the process. It'll always work out. Just follow that process through, and hopefully you'll be able to come up with the answer to the particular problem. All right. So now I want to do this problem here, which all these problems are in the packet that I'm posting today, and you can look at them. And this problem here, we're given this particular graph of f prime, and we're told that the function f is differentiable for all values of x with f of 0 equal to 6, f double prime is 0 is equal to 1/4. A portion of the graph of f prime, the derivative of f, is shown in the figure above. The boundary regions of R and S have areas of 1/2 and 5/8 respectively. Now, the thing here is this is part E of this particular problem. And I just want to highlight that on your AP exam, right? This is technically the whole problem here, where there was a part A that asked you to find Euler's method. There was a part B that asked to find a tangent line approximation, a part C that asked to find a second degree Maclaurin polynomial, a part D that you're asked to evaluate this definite integral, but in the process, you're dealing with this series. And so, like, this is, just trying to give you ideas of what you're going to be thrown at on your exam, but basically they're going to throw a hodgepodge of different things into a particular question that's going to test your ability to do different things in a conceptual manner. And so this part E, what you're being asked to find here is the average value of f prime of x over the interval from 0 to 6 is 1/2. We're asked to find the exact value of f of 6. So, all right, the reason why I want to do this problem is that we did learn this year, how do you find the average value to any particular function? And if you recall, the average value of f of x on the interval from a to b was always equal to, and this is just a formula, it's 1 over b minus a times the definite integral from a to b of f of x dx. That's just a formula that you should be familiar with anytime you're asked to find the average value of any particular function. So I'm going to use that initially to set things up to ultimately help solve for this particular problem to find out what f of 6 is. So the interval here is from 0 to 6. So I'm going to start off with 1 over, and I'll do 6 minus 0 times the definite integral of my definite integral from 0 to 6. And I want the average value of f prime of x, so that's going to be my integrand. All right, so now we know that this is our setup. And so I'm going to simplify things down just a little bit. We can say 1/6 equals this particular definite integral. And now the other thing that we knew, and I should have put this in from the get-go, is we were told that the average value of this function is 1/2. So I know that the value of all this should be equal to 1/2. And that's going to help us ultimately solve for f of 6. Because to bridge the gap from going from this average value calculation to ultimately solving for f of 6 is that, notice, to evaluate this definite integral, one way that we do that is by using the fundamental theorem of calculus, which says that we find the antiderivative of this integrand, and then we plug in the 6 first and the 0 second into that antiderivative. And if we do that, we can when we do that, we're going to get essentially something that will allow us to solve for f of 6. So before I do that, actually, because to make my life a little bit easier, I'm going to multiply both sides by 6 to get the definite integral from 0 to 6 of f prime of x dx is equal to now 3. And now I'm going to evaluate this definite integral using that fundamental theorem of calculus, and the antiderivative, right, the antiderivative of f prime of x, right, well, that should just be f of x plus some constant. And so with that being our antiderivative, I'm going to plug in the upper limit of integration of 6 first into my antiderivative, plug in my lower limit of integration of 0 into my antiderivative second, and this should equal 3. And then we were told f of 0 was equal to this 6, and so we know that f of 6 is equal to 9, and we have the solution to this particular question. So now let's look at one last problem. In this question here, we have the function g has derivatives of all orders at x equals to 1. The second degree Taylor polynomial for g centered at x equals to 1 is, and we see this second degree Taylor polynomial. In part A, we're told let t3 sub 3 of x be the third degree Taylor polynomial for g centered at x equals to 1. If t sub 3 of 2 equals to 3, meaning third degree Taylor polynomial evaluated at 2 equals to 3, find g triple prime of 1. So this problem is really just an application of being able to work with your Taylor polynomial formula ultimately to solve for this here. And what I've already done here is I've written out the basic structure that we use to construct any degree Taylor polynomial, right? And so the basic idea is that the respective derivative always equals the same power of x, and that's always over this factorial. Now, to perhaps get the third degree Taylor polynomial, I claim that's not going to be too terrible because we can pretty much just work off of the second degree Taylor polynomial, right? Because the way this formula is structured, technically for our third degree Taylor polynomial, we need everything up to x squared first, and then we add on the x to the third term. So our third degree Taylor polynomial would be equal to this 4 minus 2/3 x minus 1 plus 5 halves x minus 1 squared. And then now we're ready to set up our x to the third term. And right, the x to the third term will have g triple prime of 1 because 1 is where we're centering our polynomial at. This should be over 3 factorial, all times x minus our centering point of 1 cubed. And there's our third degree Taylor polynomial formula, which we can now use this to solve for g triple prime of 1. Because we were told that when we plug 2 in for x, we should get 3, and that should, again, equal this whole thing here with 2 plugged in for x. So I'll go ahead and now plug that 2 in for x. All right, and the nice thing that happens here is that 2 minus 1 is essentially 1, so we're going to basically end up with 4 minus 2/3 plus this whole thing here will become 5 halves, and then our last term will be this g triple prime of 1 all over 3 factorial, which is equal to 6. And to perhaps really help with solving this, I am going to make everything in here into a fraction over 6 because that is the common denominator amongst those fractions there. So we're going to have 18 over 6 equals 24 over 6 minus, this should be 4 over 6 plus that will be 15 over 6 plus g triple prime of 1 over 6. And basically what we end up getting is that 18 should equal, that's going to be 20 plus 15 is 35 plus g triple prime of 1. And we end up that g triple prime of 1 is equal to negative 17. Right, so that's pretty much it. Just some odd topics today. And again, just trying to show you the nuances of what, maybe what curveballs may be thrown your way. I hope that this video helped you guys understand, once again, Eulers method, the average value of a function, and re-examine your Taylor polynomials. As always, please continue to send questions my way. I'll try to get back to you as quickly as possible. And as always, please take care, stay safe, and I'll talk to you soon.